Okay, so now let's look at the third practice exam and go through the problems that are applicable to your second midterm. So we'll start with number 7 on this third practice exam. A 20 milliliter sample of 85 millimolar potassium hydroxide solution is titrated with the same concentration of perchloric acid. And so this is a question dealing with what is the pH at various points. So the first thing to take note of before we do anything is we are dealing with a strong base, and perchloric acid is a strong monoprotic acid. So what this means is that right away, if there's no weak acid, there's no measurable equilibria, which means that all we're dealing with here are negative logs of concentrations and partial or complete neutralizations or whatever we have to deal with. So which makes the math a lot easier, which is also why you're only given teensy amounts of space to do this, because there are no ice tables. All right, so the pH of the analyte before the perchloric acid titrant has been added, and so the analyte is this, and so if we assume, and we can, that potassium hydroxide is an ionic compound, dissociates completely, which means the concentration of potassium hydroxide is the concentration of hydroxide at equilibrium, which is 0.085 molar. So we can get the pOH by taking the negative log of 0.085. And again, calculator, 0.085 log, negative 1.07, which means that the negative log of that is 1.07. So if that is the pOH, then the pH is going to be 14 minus the pOH. So that negative quantity, I can just add that to 14 and get 12.9. So pH 12.9. Now the pH is the equivalence point. And so you can go ahead and calculate how many moles of analyte you'd have and what's the volume of titrant that you'd need to reach the equivalence point, and spend 3 pages of algebra, or recognize that because it's a strong acid titrated with a strong base, that at the equivalence point, all you're going to have is a potassium perchlorate salt, which will be pH neutral, and so therefore the pH is just simply 7. All right, what is the pH that this titration will approach as the titrant is added well past the equivalence point? So again, let's just OH equivalence. So the titration curve is going to look like that for strong acid being titrated, strong base being titrated with strong acid. So actually, apologies, it's going the other way, right? And so the pH that it's approaching asymptotically is what this question is asking, and it will approach the pH of the titrant. And so it's the same concentration of perchloric acid titrant as it is the concentration here. And so as we continue to add and add and add, what it will approach will be the negative log of the titrant concentration, which is 0.085, and we've already actually done that math up here, so it'll be 1.07. All right. Question 8, use the titration curve shown below for the following questions. So the analyte is, so what are we titrating and what are we titrating with? And then pH questions. And so again, we have to remember what the shapes of these curves look like. And so if we didn't have this little hitch at the beginning, that would certainly perhaps look, at least shape-wise, like a strong acid with a strong base. But we probably recognize that it isn't, because the pH at equivalence point halfway through is above 7. But because we have this feature here, clearly that is the characteristic titration curve shape for a weak acid. So the analyte is a weak acid. Mark the half equivalence point with an X, and so the equivalence point is easily recognizable here, halfway there. So 20 mils of that titrant 40 mils is the equivalence point, then halfway there, 20 mils or halfway through the buffer zone would be the half equivalence point. At which of the following pH values would a solution containing the analyte make the best buffer? So again, the buffer zone is the flat part of this titration curve, where you can go quite a distance in one direction or the other on the x-axis and have but a marginal distance here. And even though I've sort of overwritten it there, the pH that's closest to that buffer zone, 8 is way above it, 2 is way below it, 6 is still sort of a little bit outside of it. You know, you could make the argument, but best buffer, 4 is right in the middle of that buffer zone, so pH 4. So this is probably acetic acid, right? Or something like that. Okay, to a 0.5 liter solution, 500 ml solution of 0.2 or 200 millimolar hypobromous acid, a pKa of 8.70, initially buffered at 8.90, was added 35 nanomoles of hydrochloric acid. What's the final pH of the solution, assuming no volume? Okay, so this is a use of buffer question. And so before we can answer that, ultimately we are adding hydrochloric acid to an existing buffer solution. So chemically, this is going to need to be neutralized with our A- species. So we can't figure out the final pH until we know at the initial pH how much A we have and how much HA we have. And we do that with the Henderson-Hasselbalch equation. And so the pH, 8.90 equals the pKa, 8.70 plus log of A over HA. Subtract 8.70 from each side. 0.20 equals log of A over HA. 10 to the 0.20 equals A to the HA, HA, and then we get that ratio, putting that in our calculator, 10 xy 0.2, we get 1.585 as our A to HA ratio. All right, now again, we'll make this point. The concentration given, even though it's phrased 0.2 molar hypobromous acid, that is not the concentration of hypobromous acid. That is the concentration of hypobromous acid plus the concentration of hypobromite, the A and the HA species combined at that particular pH. So we do not plug in that concentration for HA and solve for A. Again, this is the mistake people tend to make. Instead, we're going to set up our mole balance reaction, or mole balance equation, where A plus HA. And I'm going to do this in moles rather than molarity, because we're looking for a mole that we can add afterward. And so given that the Henderson-Hasselbalch equation, which is where we're starting and where we're going to be finishing, involves a ratio of molar concentrations, the volumes would cancel, we can do these in moles. So 0.5 times 0.2 is 0.100 moles, right? So that is 0.100 moles. So now we have two equations. A over HA is 1.585, A plus HA is 0.1 moles. And so again, I can turn this one into A equals 1.585 HA, and then plug that in down here. 1.585 HA equals, plus HA equals 0.100 moles. So this will be 2.585 HA equals 0.100 moles. All right. So calculator, I already have the 1.58 in there. I'll add 1 to it. And then I will take the inverse second function here, and then I'll multiply that by 0.1. And so that will give me my HA quantity, which is what that equation solved for, 0.0387. And now the A, which I'll have right there, I'll just say equals, is going to be the difference of the total quantity of moles, 0.1 in that. So I can do that in my head, 0.0613. And these are both in moles. So if we were to put these in millimoles, this would be 61.3 millimoles, and this one would be 38.7 millimoles. And we do that because the amount of hydrochloric acid we're giving in the second part of this equation is in millimoles, so it would just be easier if we put it there. So in order to come up with the final pH, Henderson-Hasselbalch equation again, pH equals the pKa, that's a constant, does not change, 8.70 plus log, and now we have the original amount of A minus, which is 61.3, and the original amount of the HA species, which is 38.7. And again, we can do this in moles, millimoles, molar concentration, whatever, because the conversions in the numerator and denominator cancel each other out. So if we are adding 35 millimoles of hydrochloric acid, we have to ask ourselves chemically what's going to happen. So that strong acid, the H plus from that strong acid, will be neutralized by the weak base that's in existence in this buffer system. That's our A minus species. So for every millimole of H plus, it will react with A minus and subtract that quantity from the total. So down below, up above, we subtract 35.0 millimole, and then every time we protonate one of those A species with a proton, that creates therefore an HA, so that same quantity we subtracted from our numerator has to get added to our denominator. Again, we're not changing the total number of moles of this hypobromous acid, we're only changing the protonation state. We went from a certain ratio of A to HA to a different ratio of A to HA, but the sum in moles should always equal the same quantity, 100 millimoles. So down below, we add those same 35 millimoles to the denominator, and then all we have left is the calculator work. So up top, 61.3 minus 35. So our numerator is 26.3. I'm just going to write it over here, 26.3. And down below, since they have to add up to 100, I can just do that in my head, 73.7. Right, so now I divide 26.3 by 73.7, 73.7. So that's my new A to HA ratio. Take the log of that. So that's now all of that, and I can add that directly to 8.7, which is the pK. And I'm going to get a pH of 8.25. All right, and that's all from exam 3, the practice exam 3 that will be on the second midterm. Please let me know if you have any questions.